Elementary mechanisms of deformation in amorphous solids from 0 to low temperature.
So, yes, thank you to the organizer for inviting me here. I will be the one not to talk about nucleation, neither aggregation nor growth. I'll talk to you about something which comes from a different domain, which is plasticity, and the question that we have in mind are what happens when we deform a material. I think the connection, you'll see that some connections exist, essentially because plasticity reveals mechanisms which are important in more general contexts. So this work is a work which has, what I'm going to talk about has been mostly done with Christian Karolif in the last years. And the last part of my talk, and I'm not sure I will have time to go there, is the part of the PhD project of Joyji Chattaraj, who is here, who is also presenting a poster. So if there are any questions on this part at the end, I'll refer you to his poster. So because I'm not talking about nucleation specifically, I'd like you to interrupt me if there is anything unclear. I don't want to rush. I don't care about going through all my slides. What's most important is that you can just grasp the main important points. So don't hesitate to interrupt at any time. Yeah. So the question that we have in mind is to understand what happens when amorphous solids are deformed. And amorphous solids essentially are glasses or solids which have no structures like here. And this is in contrast with the situation of crystals. And you know that in crystal, it has been identified now for decades and nearly a century that the plastic deformation of crystals is due to the motion of a kind of defects which are called dislocations. Dislocation can be seen experimentally, and it's just by the and they are, I mean, they can be used to construct models. I mean, their interaction and motions are understood, and starting from this, it's possible to, for example, to have computer models of dislocation dynamics. The problem is when you go to something, let's try to go this way. When you look at an amorphous system, there is no order, and because there is no order, there is no dislocation. And the question then is to understand what happens and how can we construct a theory of deformation. And if we want to construct a theory of deformation, we need to identify the elementary mechanisms that are responsible for it. But without, are there defects? Something like dislocations or not. So when I speak of glass and amorphous solids, I think of a very large class of materials, in fact. You can count hard glasses and soft glasses. Hard glasses would be metallic oxides, polymers, and these are glasses which are made of systems with length scales smaller than nanometers. Energies are in this order, and that introduces stresses which are in the range of gigapascals. If now you go, there is a lot of interest recently in soft glasses which are colloids or foams, and of course here the length scales now are larger. The energies are essentially set by kT, and that gives you stresses which are a lot smaller. But the idea in the field is that these systems probably deform in very similar ways once you rescale correctly the appropriate energies and lengths and stresses. And so the question is, one of the questions is, okay, even if we identify some elementary mechanism of deformation, would they be general enough to apply both to metallic oxides, say, and colloids? And if we understand this mechanism, maybe we can start to say something about that. Here, just for the picture, this is an indentation. This is a compression test on a metallic glass, and I will speak a bit more about metallic glasses. And where you see here that you have some formation of what we call a shear band when we compress it. So what we want to understand in the long run is this type of curves. That's typically a stress-strain curve. On here, it's PMMA. So essentially, you take a PMMA sample which has been prepared by some appropriate, by some well-characterized way, and you strain it, and you have this stress increase, and then the system goes to some kind of flow stress. And these are very similar curves which are here obtained for metallic glasses. And you see the same kind of curves. What I'll focus on in my talk will not be, in fact, the loading part, which is perhaps the most important part for engineers. I'll focus on what happens in steady-state conditions, in steady flow conditions, because that's where we can start to, we have a well-controlled system, and we can start to understand what's happening. So just a word about metallic glasses. Because probably many of you are not familiar with metallic glasses, and they are a very exciting kind of material. In fact, a lot of what we know in plasticity of amorphous solid has been developed within the community of metallic glasses, essentially because these are materials which just motivated a lot of interest. Just to show you an idea, that's a picture I like to show when I give a class. This is a Cassini spacecraft after landing, so it went to study Saturn's and crashed in the desert. And on this thing, you had a piece of metallic glass, which after the crash here is just still, shiny and barely touched. So what is a metallic glass? So just for, for those of you, since, okay, that's my one slide on nucleation. So what is a metallic glass? A metallic glass are some very, very complicated compounds of metals. And the reason why they are complicated is to be able to have something that, in the TTT diagram, to be able to have something that will not crystallize over reasonable timescales. You know that if you want to avoid crystallization in a normal metal, you will need quench rates which would be in the order of the 10 to the 9 K per second. If you want to achieve reasonable cooling rates in order to avoid crystallization, you need to create compounds with very complex formula because essentially the system will not manage to find its very complicated crystalline structure. So these metallic glasses here, just to show you why they interest people, essentially they are harder, they have higher strengths than steels and larger elastic limits. And their big problem, and here that's again a sample of metallic glass which has been which is then compressed. And the big problem is that they are brittle. And the one thing we want to understand is the emergence of shear localization that we see here. Essentially, you compress a system, and the system will start to localize and crack along one band. And the question is how this happens. Okay, so that's the general idea, and okay, I'll pass on this. And so the idea which was motivated by that, Ali Argan in the late 70s proposed that, in fact, what Ali Argan did, he looked at a test on a bubble raft. So the idea is that to have a raft with bubbles floating on top of some water, and he sheared the bubbles and just looked. And from these experiments, he concluded that the deformation was just due to local shear transformation. The idea is essentially we can say nothing but the fact that plastic deformation is a bunch of rearrangements. And so that's the kind of thing, that's what I think of a rearrangement. It's a bunch of particles which then are transformed into some different configuration. It's not much, but that's essentially, and the idea that the macroscopic plastic deformation is the addition of all these things. This is very analogous to something that is called the T1 process, which occurs in foams. In foams, for example, this is experimental images of a foam where you have 4 bubbles which will rearrange here. And essentially in foams, because essentially for topological reasons, the only way a foam can rearrange is via these T1 processes when you have 4 bubbles which are exchanging their neighbors. So that's the idea. The idea is that you have these local shear transformations, and I'll pass on that. I don't go into details, but the point then is that most theories of plastic deformation since then were just trying to write constitutive equations, and they essentially write here, this is a strain rate, and they try to write the strain rate as a function of the stress. The stress doesn't appear here on this slide. It's contained into into transformation rates. And the idea is simply to say, okay, we know that there are these many local transformations, so we need to write an equation when we say that the strain rate is just the sum of all these events, and we just try to guess or to write a theory for what is the rate of these events. And the problem is that in all these theories, these local shear transformations are assumed to be independent. They're just thinking that, okay, they are local shear transformations. We try to write rate equations for these shear transformations. And the big problem, and that's where, in fact, that's something which comes from works in Martensitic transformation, is that we know that when a rearrangement occurs, it might couple elastically with the rest of the system. So, okay, in fact, this is an idea which comes from Eshelby, and initially which comes from Martensitic transformation. So the idea, okay, in the context of a Martensitic transformation, what you have is that you have, say, a metal, and inside you have a change of a Martensite, which essentially a part of the metal, which will rearrange because essentially it's changing. Usually what it is that it goes from one crystalline order to another crystalline order for thermodynamic reasons. So you have a piece of a material which is changing its natural shape. And the point is that this piece of material is, of course, connected with the rest of the system. And as this guy will change its shape, it will introduce stresses in the rest of the system. And now these stresses, there is the Eshelby calculation, which just explains how to compute these stresses. And what it will do in this case, it will essentially, if this guy is transformed in this direction, so in all this talk, the idea that the notation that I use in these kind of drawings, the system is sheared like this, in this direction. So it's simple shear along these directions. And when you have a simple shear, it corresponds here, this simple shear also corresponds to shear which is in these two directions. So essentially, this guy is just shearing along the main principal axis of the strain. And the point here is that it needs to couple elastically, and that will introduce stresses. These stresses can be computed in various ways. An idea to see that, instead of looking at the change of an inclusion, is to think of point forces in a very point-like source in a material, and they give rise to displacement field and stresses which have forms that can be calculated at long range, because it's just an elastic property. Okay, so the problem now is that when you have a rearrangement, this rearrangement will introduce stresses, and it is then possible that it will trigger another rearrangement. If this occurs, it means that the assumption that these rearrangements are independent events is no longer valid. And the first question we'll ask is whether these rearrangements can be thought as independent processes or not. So, in order to do this, in order to study plastic deformation in this system, in the amorphous solids, I'll use numerical simulations. And there is one problem in numerical simulation. The problem is that the typical Lennard-Jones time is something like 10 to the minus 13 seconds, which is extremely small. Which means that in simulation you can at best access this, and when you want to strain a system, if you want to achieve a deformation which is, say, of order of 100%, then you have to access strain rates which are absolutely huge. In order to bypass that, the idea was essentially to construct a numerical protocol where we could do things differently. And in order to bypass that, if you think of now a glass which is at low temperature, meaning it's well below Tg. A glass well below Tg will essentially all the time, will essentially be in one local minimum in this potential energy landscape. And if it's well below Tg, the alpha relaxation time is huge, and it means that this system will essentially never leave this local minimum. Now, when you deform a system, at some point, you will allow this local. So this is essentially a solid. That's my picture of a solid which is in a local minimum. And now, if you deform a tiny bit this system, what will happen, you will deform the minimum, and the system will just follow. And if you deform a bit more, it will continue to follow this minimum. And this is reversible. You could go backward, and the system would just go backward along exactly the same configuration. At some point, the minimum in which the system is located must lose stability. When it loses stability, the system then needs to find a new local minimum, and then it will actually, that's when it will dissipate energy. This is in fact something that is known since for a very long time. Essentially that when you shear the fact that you have a yield stress. So yield stress means that when you shear a system infinitely slowly, you will dissipate energy. You dissipate energy when you load your system infinitely slowly, which means that your system is always adiabatically adapted. It's always in the local minimum. And the dissipation must come only from very fast, unstable events. The question is what? So when you do this shearing, this very slow, so numerically, this type of protocol can be implemented by simply minimizing the energy. So you take a system, you minimize its energy, it's residing in a local minimum, you strain a little bit, and you minimize again. And if you strain only a little bit, you will follow continuous changes in a local minimum. So and from time to time, the system will lose stability and reach another minimum. And you arrive at some, if you plot, for example, stress versus strain, the system produces something like this, which is a serrated curve. And the branches here, the ramps, corresponds to the elastic loading. And the drops corresponds to any drop corresponds to a situation when the system has reached instability and has had to fall in search of a new local minimum. Okay, so the kind of simulation I'm using is something that we call the Lees-Edwards boundary condition. So essentially you have a cell which is a square cell. This cell is symmetric, so this edge is the same as this edge. It's symmetric here. And now it is symmetric also here, but with a slight shift. And this shift increases, and by increasing the shift, we introduce strain in the system. And we introduce strain in a way which is translationally invariant. And that's a way to avoid a lot of boundary effects that would be found in experiments. Just for the sake of completeness, we've used a variety of potential interactions. I'll mostly show you, I'll show you data mostly with Lennard-Jones systems. Okay, so essentially these athermal because T is 0, quasi-static because the strain rate is 0, simulations produce this type of curves. And of course, you just need to be very cautious, use very small steps to resolve the elastic branches. And the question is now to understand what happens during these plastic events. Yeah?
So you have only the strain comes in only from the boundary?
That's all. Absolutely.
So you don't have body forces?
None. What I do is that when I strain the whole system linearly. But it changes nothing when I'm in the elastic response because the minimum is just changing. I mean, I'm just tracking local minima. Okay? So these are plastic events. And the question is, what is a plastic event? Is this plastic event one rearrangement or something else? Is it this Eshelby-like shear transformation or something else? So if we look here at these rearrangements, what we find here now, so we take one of these rearrangements and we look here at energy versus, so here what I have, right now I have no time. I will come back later with time. So here I'm just minimizing this energy. S square is just the energy dissipation rate, and you see that the energy dissipation rate is very spiky. It's very spiky, it has bursts, and energy descent is very intermittent, and that should tell you right away that this energy release process is not a simple process. It's not one simple shear transformation. It cannot be because it's something much more complicated. Now, if you look at the very beginning of one of these events, and what I'm doing, I'm just taking a configuration which is there at the beginning and a configuration which is there just at the end of the plateau. So I'm really looking at the onset of this instability. And here what I plot is a difference in energy between these here and there configurations. And what you see here is that essentially you have one local shear transformation which is occurring in your system. So if you look at sub-intervals along this path, you will find local shear transformations. But now, if you look at, if you look at the whole process of these descents here, you find that this whole process, in fact, the gray part, that's my whole system. That's a system with 50,000 particles. The gray tells you when something happens, and you see that you have a cascade. So one plastic event is not one shear transformation, but it's a cascade of shear transformations. And now this cascading effect can be characterized, for example, by looking at the energy drop statistics. And the energy drop statistics in 2 dimensions, you find that these energy drop scales like L, where L is the side of the system, and in 3 dimensions like L to the power about 1.4. These are not normal statistics. These are not the statistics you would have if plastic events were just local, independent events. So clearly there is an avalanche mechanism, and this avalanche mechanism is the proof that the Eshelby effect is there, that these local shear transformations are talking to one another. If they were not, you would find normal statistics. So just to understand what gives rise to this avalanche mechanism, the first thing is that, so this is back to my slide with Eshelby. So from Eshelby, we know the form, for example, of the displacement field. We know the form of the stress field, which has this cos 4 theta. So there have been measurements of these, and for example, here this is a displacement field right at the onset of a plastic event, and this displacement field, we analyzed it by doing Fourier transformation to find that indeed we recover the 1 over r square, which is predicted here. You have x, y, r, 1 over r. So we just recover the 1 over r, which is predicted by Eshelby. And this is another work where people just looked at one isolated event. From time to time, you manage to see one isolated event, and they do find the correct cos for theta, essentially, which tells you that here you have 4 lobes of the stress where the stress is increasing, the shear stress, and 4 other lobes where the shear stress is decreasing. So these Eshelby patterns are well characterized. I'd just like to do one parenthesis at that point, because I need one tool just to try to continue. I need one tool to show you, because I want to talk about softness in the material. I want to be able to tell you that there are some regions in the material which are softer than the other ones. And to do this and to characterize that, one way to look at soft regions is to look at just what we call the non-affine displacement field. What is a non-affine displacement field? Essentially, what you take one system like this, and if I deform it, and here I'm just deforming it homogeneously. So everybody is just deformed by, okay, just here it's just a simple shear. But if I was here at equilibrium, when I deform it homogeneously, I'm no longer at equilibrium. I'm no longer at the local minimum. So if I shear homogeneously and then minimize the forces, I arrive at slightly different configuration. What I do now, I will subtract this affine part. The affine part was this part. This was affine. This is my new minimum. And now I reverse backwards, just to subtract the affine part, because there is this trend here which masks a lot of the information. When I subtract, I just find some kind of displacement here, and these are the non-affine displacements. And you see here that things are moving much more here, for example, than there. It tells you here the system is softer than there, and that's for a small system. If I do that now, I just here replace these segments with arrows, and that's what I have. And if now I do this on a bigger system, this is what I have. So these non-affine fields are just a way to measure softness. Here you see that when you have a lot of black, you have soft regions. And what we can do to observe this Eshelby mechanism, we actually can look at this non-affine field. And this here you see this is a small system. This is the non-affine field at some strain, 556. And you see here that, again, if you look here, the arrows here are going in, the arrows here are going in, the arrows here are going out, here they are going out. So it's, again, a local shear transformation. So here you have a soft shear transformation. Between 556 and 558, this guy will actually transform. And here you see that the transformation has taken place, and now the system is totally wiped out of any softness. And what is important here to see that as this guy has triggered, it has actually loaded another one. So you can actually see the effect that you have one rearrangement, and this rearrangement will, in fact, so here you had a system which was soft, and now this system is softer. It is softer because it was near an instability threshold, and this loading just pushed it even closer to the instability threshold, and that's why it now shows up as bigger arrows. So the point here is that what we learned from the AQS simulation, we learned that first plasticity results from local shear transformations, but which are not isolated events, which are actually first they are not isolated. In fact, their plasticity involves avalanches of these local shear transformation. And the reason why you have avalanches, there are two reasons why you have avalanches. One is that this Eshelby mechanism tells you that as soon as you have a rearrangement, it will load the system farther away. So you have this possibility to have communication between rearrangements. And the second reason is that when you shear a system, you're actually bringing progressively these zones toward the thresholds. And so you're making a system, you're creating a system where you have many, many, many soft, very near unstable regions. So now, because you have many regions which are near instability, as soon as one rearrangement, just emits these Eshelby stresses, it will modify the stress in a system which is very weak, and that will create an avalanche. Okay, so the question then, okay, so that's what we learned from doing this AQS simulation. And the problem with this AQS simulation is that temperature is 0 and strain rate is 0. And so the question, of course, is, okay, now we need to go back to the real life and try to understand what happens in a real system which is sheared at a finite strain rate at a finite temperature. So going to finite strain rate and finite temperature immediately is too difficult, because it means that I start from two parameters which are 0, and then I need to have two parameters which are non-zero, and I don't like to do that. So the way we looked at this, we started to go to a situation. First, we looked at the situation when temperature is still 0, but the strain rate is no longer. So now we'll focus on system where we still have a 0 or very low temperature, but now non-zero strain rates. The problem is that when you shear a system, when you deform a system, you are working on your system, so you're injecting energy in the system, and if you want the temperature to remain 0, you must find a way to extract the energy. There are various ways to do this. There is one way which is in fact correct, and which is essential. Okay, so we do this by introducing essentially dissipative forces. So on each pair of particles, we'll just introduce a viscous drag force. And this can be done in various ways. And the correct way is to introduce here viscous drag, which is just related to the velocity difference. And the reason why this is correct is because this guarantees that you propagate sound correctly in your system. If you have okay, there are other ways they don't propagate sound correctly. Here, in this case, sound will propagate correctly. The damping parameter here essentially sets a length scale, which is the length scale below which the waves are overdamped. And the large wavelengths, the point here is that the long wavelengths are not damped. The short wavelengths below these lengths will be. And what we choose here, we just choose a length, a typical length, which corresponds to what we think of a zone size, this transforming region size, which is about a few particles. And so the question is, what happens now when I shear a system? And do I continue to see this shear transformation? Will I continue to see correlations between these shear transformation? Do I have the idea? Should I think that there is still these Eshelby stresses are continuing to be present? Will I find avalanches? So in order to do that, the first thing we look at the velocity field. I spoke to you before of the non-affine field. The non-affine field was looking at the elastic response. Now it's, in some sense, it's simpler. I'll just look at the velocity field. But again, I will subtract from the velocity field, the affine part, which is the trivial part, because this, of course, the velocity, if I shear a system, the average velocity field is just a linear profile. So I subtract the linear profile, and we just look at the non-affine part of the velocity field, the one which contains information. And this is what we see. So these arrows tell you how the system is sheared. And what we see, in fact, is that, so first of all, we see tons and tons of shear transformation events. So all these, here you see that, okay, everything I plot are arrows. The reason why when you have some kind of shades of gray is just because you have very tiny arrows. And the variety of shades just tell you when you have larger or smaller arrows. When you have very big arrows, it's because in the center of this rearranging region, there are few particles which move like crazy. And so they produce very big arrows. But essentially, these regions, these big quadrupolar-like patterns, just corresponds to local shear transformation. And you see they come in very many types. Some rotate a little bit. The point here is that when you have this shear transformation, you see that shear transformation emits information, which then propagates away. What you see here, now look, you see these waves which are propagating. In fact, they are waves. They are, in fact, shear waves. And we know the shear modulus in the system, so we know the sound speed. We know all the moduli. We know, and these waves actually are propagating at the shear wave speed. So they are really shear waves. So what you see is sound. It's sorry? Ha! Where do they occur? This we don't know. This we don't know. This is the big question. I mean, should we identify a defect? Are these shear transformations related to some kind of defect? That's a question that everybody asks, and there is no convincing answer. Because the problem is that this structure is very disordered. So the only thing I'll do here, I just know they are there. I just know they are shear transformations, and that's all. I'll not use more than that, because as soon as you start to say the shear transformation occur here or there.
No, sir, what I mean to say, we give some defect in some point, and we try to shear the system, whether it will start from where we can predict this will start.
The problem, yes, okay, there are ways to try to predict that. The problem is that people have tried to relate this shear transformation to high stresses. It doesn't work. People have tried to relate that to low densities. It doesn't work. In fact, a shear transformation is a property of the local modulus. It's a soft region. It's more than a property of the modulus. It's a region which is soft and softening. So it's a properties of the higher derivative. It's something very complicated to measure. And so it's not something that you can relate directly to a very simple structural property. Okay, so, yeah.
Sorry, I thought for a given structure, you can measure the higher derivatives and predict when...
Yes, we can.
Yeah.
But we need to go to high derivatives. That's what I'm saying. We can do this by measuring the high derivatives, but we need to go that far. We cannot find shear transformation by looking just at stress or density. Okay. So now what we see is that we continue to have the elements which were responsible for avalanche behavior. We continue to have shear transformation. We see these shear transformations, they are indeed elastically coupled. They even emit elastic sound waves. Or from time to time, we didn't see that maybe on the movie, but from time to time you can see that one will trigger a second one. This is something that you actually see if you look closely at this movie. So there are correlations between these events. But now the question is, do they actually make avalanche behavior? And under what conditions at a finite strain rate? And to do that, what we looked at now is we looked at the strain field, which is the simplest thing to look at. So here we just take a system, and the system has been, that's the macroscopic strain, 1, 5, 10%. So you strain your system, and during this macroscopic strain, we look at the pattern of local deformation in this system. And now what you see is that there are huge correlations in this pattern. This is far from something random. It's something extremely structured, and it's very directional. And this directional correlation only comes from the fact that you have these Eshelby-like shear transformations. But the problem then is, how do you characterize avalanche behavior? When we were in AQS limits, we could just look at plastic events by looking at the statistic. When we wanted to be quantitative, we could look at statistic of stress drops or energy drops. We could do this because essentially in the AQS in these AQS limits, you have continuous branches and there's discontinuous drums, and they are very easy to identify. Now, the point here is that as soon as you start to go at a finite strain rate, if you look at your stress versus strain curve, it will start to show some kind of things like this. And this here occurs because you remember I showed you that the energy descent is very intermittent. Very intermittent means that there are times when nothing happens, or barely. The system is not stable, has not found a minimum, but waves are just propagating, but it's just propagating. And it's not, there is no dissipation. And if you have this type, during this time of time, as you are at the same time loading your system, this shows up as some kind of things like this, kink like that. And the point here is that now if you look at your stress fluctuations, for example, you lose the signal, you very quickly lose the signal that tells you whether avalanches are present or not. So the question then is to find a good observable to characterize avalanche behavior. And so what we did, and that's what we did here, was we looked at the diffusion, the transverse diffusion. So we learned this again from AQS. In AQS simulations, so again we share our system, same with my Lee-Edwards boundary conditions. Y is this axis, and here I'm just looking at the diffusion, at the fluctuation of displacement in the Y direction. I like to plot it directly as a delta Y squared divided by delta gamma. This is in AQS simulation, so there is no time. So the only thing which looks like a time is the strain. So I need to divide by delta gamma. And of course, if you have diffusive behavior, it means simply that this should reach a plateau. And that's what you see, that you just see that this coefficient reaches a plateau. The problem, the surprise, is that this plateau is extremely system size dependent, which is not what you should expect from diffusion. It is system size dependent because the system is elastic and there are elastic interactions at long range. Okay, so we have this strong system size dependence, and so what we did was we looked at, again at these finite strain rate simulations, we looked at the same thing, and again we find a very strong system size dependent. This is for a finite strain rate. Any strain rate in simulation is huge compared to anything you access in experiment. So the AQS limit corresponds to the true zero strain rate limit. This 10 minus 3 corresponds to a huge strain rate for any reasonable experimental time scale. So the experiments are somewhere in between. The real life is somewhere in between. The point here is that I can find the same behavior here as I found in the AQS limit, which tells me that this continues to be relevant over a huge range of strain rates. So now what we do essentially is that we take the plateau values, and we look at these plateau values for a variety of strain rates. So here my only parameter is strain rates. And what we find here, so the arrow here tells you when you go to the lowest strain rates. And there are 3 points here which corresponds to AQS data. What you see here is that for the very low strain rates, you have this d hat, which is this plateau value, which is almost increasing linearly with system size, which suggests again that there are avalanches which are linearly increasing with system size. Now, if you look at the higher strain rates, you start to lose this behavior. You start to lose this system size dependence. And you start, in fact, if you plot now d hat versus log L, you find something which is almost a log. So essentially, we have diffusion constant, which has a log at large strain rates, and which is almost linear at small strain rates. near the quasi-static limit. So how can we understand that? Okay, so that's okay, a little bit more technical. So the idea we have is that precisely as you asked, where are the flips? We don't know where they are. The only thing we know is that there is a number of flips. We know that when we need to strain the system, so we know that we'll think that we know that they are flipped, they are broadly distributed, and we'll just pick a characteristic strain and a characteristic size for these objects. And then we know that each flip releases a stress, which what is important here is that this stress is just some constant divided by the volume of the system. That just tells you have a local event. It releases a fraction of the stress, which is just the 1 over L square fraction. So over a long strain interval, you will have a number of flips. Each flip releases on average this stress, and this should be equal to how much you ramp up the stress by shearing. And all this tells you simply that the number of flips is just proportional to the to the volume of the system and to the strain. All this is very normal. I'm just saying that in fact, I'm just saying that I have a number of flips, I have a density of flips in terms of flips per unit volume and per unit strain, which is just a way to state that these flips are, these rearrangements are local. So, once I've said that, how can I understand diffusion? Essentially, if you take one particle and you look at the displacement of this particle over a long interval, you look at all its motion. And this particle moves every time there is a plastic event somewhere in the system. The point is that the plastic event can be far away, but it will still disturb a little bit this particle. So here I'm just saying that the displacement of this particle is just the sum of all the flips. F stands for flips, so for rearrangements. And on all the flips of the displacement at this point, Ri, due to a source, due to an Eshelby event at Rf. And now when you do this, this is just now, if you assume that the flips were independent, you know they are not, well, you arrive here at an expression for delta y square, and okay, I just passed the details. We just here arrive at an expression where we have a log L. And the log L comes from elasticity in 2 dimensions. Now, so that explains the parts, what happens at high strain rates. And essentially, the idea we have is that at high strain rate, these events will be decorrelated. Now, it also tells you that if you go to low strain rates, you must have correlations between the sources of plasticity, between these elementary events. Therefore, you must have avalanches. So we look again at this pattern, and to make things simple, we will think of, we'll think of these flips as just linear objects of a given size L. And we just go along essentially the same calculation. I will pass the detail. You just look at the displacement of one particle. Instead of saying it's a sum of flips which are independent, we say it's a sum of avalanches which are independent. And these avalanches have a length L. And we go through the detailed calculation of what is the displacement due to a sum of Eshelby flips aligned along a line. And now we arrive at something which goes like small l. So we arrive here at an expression for the diffusion constant, which depends on small l, which is a correlation length between these flip events. This is the expression we have. Now, in the limit where these avalanches, imagine if an avalanche contains a single flip, it's the limit where this L is just the size of one region, of one zone. If I put A here in this expression, I recover a log L behavior. Now, in the AQS limit, we had found that the avalanches were scaling like capital L. So if avalanches do scale like capital L, have a typical length scale which is only set by the system size, then we should find that d hat here, if you plug it capital L here, you find that d hat corresponds to capital L. So essentially, that's what we see. We just see that we have broad difference, a strong strain rate dependence of the diffusion constants, and this is just an effect of the correlations. Now, the problem here is to try to understand, and this, I think, the diffusion constant, okay, that's really, that's a tool to characterize avalanche behavior. What is what is really important, and I want to focus on, is what sets this L? What? Yep. Okay. Okay, I'll just go through this argument. Okay. So what sets this L? So the idea is what? The idea is that if you strain a system faster, per unit time, you have more events. All these events emit acoustic waves. So if you strain a system faster, if you look one region here in the material, the faster you strain, the higher the frequency of the noise it's receiving. And so essentially what will happen is that if you first of all, if essentially you can find, there is one natural length which emerges from that, which is a length at which, if you just take a circle of a given size L, and the number of events, the number of signals emitted from this region will just grow like L squared gamma dots. And so there's just a natural length such that these objects are separated in time. So essentially the thing is that if you look at your neighbors, you can receive signals which are separated in time. If the signals are separated in time, it means that the information they carry is something that is visible and that can introduce correlations. When the events, when the noise, when you start to shear a system faster, the noise signal will start to overlap, will start to arrive at the same time, and you will start to swamp out the information that you would have from your local neighbors. And this will set a length scale, and it turns out that this length scale just goes like here, just goes like 1 over square root of the strain rate. Okay, I pass on that. And now when you take all this diffusion data and you introduce the fact that you have this length scale which is set by sound, by noise, you arrive here at, you can rescale all your data and find an amazing collapse of your diffusion constant. So that's the idea we have. The idea we have is that this correlation length is only set by, when you strain a system, is only set by the fact that you need to see, to distinguish the signals which are coming from the farther away neighbors. That sets a length scale. And beyond this length scale, you just see noise because you are in a large system and you have a huge amount of signals which are coming up. Okay, I'll just pass off that just to tell you that this in 3D can be extended, that it gives, in fact, a very reasonable length scale and relation between length scale and strain rates, which actually correspond to what is seen in experiments. So essentially, for reasonable strain rate of 1 second minus 1, it tells you that you can have correlations up to microns. Okay, I won't go much more than that. The thing is here that, to conclude, that in the AQS limit, we found that there are avalanches. These avalanches, they are, in fact, an effect of this Eshelby stress release. It turns out that this effect continues to be valid at any reasonable strain rate in your system. And in fact, it's clearly something which is absolutely determinant for, which control the plastic flow of this material up to experiment strain rates, and very possibly, in fact, which is responsible for the shear bending instability. This is not clear whether it is or not responsible for the shear bending instability, but it is now a very good candidate. I mean, these Eshelby stresses, this Eshelby mechanism is a very good candidate to account for that. Okay, the one thing I did not talk about, I just show you briefly, because Joyjit will present you a poster on that, is what happened at finite temperature. And for that, I refer to his poster. And okay, you will see there is a data accumulation over tons of values of parameters. And the idea is that simply what you will see is that at finite temperatures, you continue to have avalanche-like behavior. And what we are doing right now is trying to characterize, to quantify these avalanche mechanisms in finite temperature systems. So for that, I refer to Joyjit's posters. Thank you.
Questions?
You know, you basically spots or soft regions
Yes.
under shear. Is the yield limit a percolation limit of these soft spots?
No.
No, it is not just a geometric, it's a dynamic thing.
No. I wouldn't say that at all.
Okay, and the other thing is these acoustic bursts, which you can, of course, these have been experimentally measured by people in Barcelona and elsewhere.
For example, yes, in Barclay's noise or in this, absolutely.
But somehow they treat their data by by chopping it up in various ways, and
Yes.
then this really requires transducers kind of scattered throughout the system. And can you comment on?
Yes, I could comment for hours on that. There is a huge amount of literature which is motivated by Barkhausen noise. The point again is that it's Barkhausen noise which happens in magnetic systems, and the problem is that what you can access experimentally is the signals from noise transducers. So there is a huge literature looking at these spikes. What is not clear to me is what is just a property of the analysis of spikes versus the physics. And I say that, I mean, there is a huge amount of literature on that, and because in some cases that's the only thing you can do. So you have to do this. Well, you have to do this. It turns out that on plasticity, because we had to look at this in a different way, we had to look at avalanches, we feel like right now we learn a lot more on our avalanche mechanism even than in other systems. But there is a lot of work on Barkhausen noise, and there are a lot of models of driven elastic manifolds. So, okay, so...
You had a slide on non-affine displacement field. So that in the slide you had particles of two different sizes. So could it be that in certain regions where the displacements are large, you actually have smaller particles
it's almost
together?
right. It's often right. Yes, often the very big arrows.
Yeah. So
not the quadruple row pattern, which corresponds to a mix of everybody, but the very big arrows at the center. Sometimes maybe small particles.
Yeah, so I'm asking, like, could that be responsible for, or could those be the points where these flips are initiated?
Oh, is it correlated with, for example, more small particles? No, I don't think so. We looked at images after images after image, and we don't see anything.
Particle configuration in regions where these rearrangement events first happen. Is it possible that they are such that the packing is kind of square-like? And imagine if you had just 4 disks, and instead of being nicely nested and forming a locally 6-coordinated structure, if you had sort of things like that, where that means they're sort of prone to failure because they're not sitting in a way in which the response will be to give you a restoring elastic force.
There are attempts to relate these flips to some particular structure. Okay, some people claim they can relate, maybe not the flips, but because they didn't look really at this regime. I don't think there is any correlation. I think you would have to. I don't see anything. But now, okay, probably that's something that could be looked at in more detail in this situation. But it's really, the point is that it's really a property of the modulus. What I think is that this flipping is a property of the modulus and the higher derivatives over a region which has 5 particles wide, so which is very broad in terms of what you're thinking of.
Okay, so let's thank Anil again.